Greetings of the day, dear students. In this video, we are going to discuss about the starting methods of three-phase induction motor, and also we are going to discuss about the break test on three-phase induction motor. Right? What are the different methods of starting of an induction motor? We will be discussed in a step-by-step manner. Right? We are having a direct online starting method, stator resistance or reactor method, auto transformer starting method, star delta starting method, and rotor resistance control starting method. So these are the 5 different methods of starting we are having. Right? I repeat again. First one is the DOL starting method, stator resistance or reactor method, auto transformer starting method, star delta starting method, rotor resistance control starting method. Right? So in DOL starting method, direct online starting method, if you observe, for the stator, the three-phase supply will be directly given to the stator without any intermediate resistances or rheostats. Right? The three-phase supply will be directly given to the stator winding. Because of this, what happens is, at the time of starting, the machine draws very high amount of current. So how do you understand that? For example, it will be about 5 to 7 times the full load current. For a short span of time, immediately, for example, if you are having, if the full load current is some 6 amps, right? At IF, the full load current IF is 6 amps. At the time of starting, IS, it can be around some 5 to 7 times. That means, for example, 5 into 6 times. That is, it will be around 30 amps will be drawn by the machine or motor. So this will be a drawback. If it is going to draw huge amount of current, all of a sudden, at the time of starting, what happens is, in the lines where it is from where it is going to get the supply, right? There will be the huge amount of voltage drop in the lines, because the current drawn is very high. Because of the already existing resistance of the line, V equals to IR, amount of voltage drop will be voltage fluctuation we can observe. That is in the form of a blinking of the lights, or some small reduction in the speeds of the fan, where other loads are also connected on the system. Such kind of observations we can make if the motor is started with DOL method. This is all because with the help of direct online starting method, it is going to draw some 5 to 7 times the full load current, that too for a short duration of time. So here, the amount of current, how much current it may draw, will depend upon the design and size of the machine. And as I told you earlier, such high starting currents, okay, will cause a large voltage drop in the cables or lines. Therefore, it is going to affect the supply to the other consumers on the same system. Now, from our previous discussions where we have derived the torque equations, the starting torque is given by ITST equals to I starting current square into R2. R2 is the rotor resistance, and omega S, synchronous speed. Now the full load torque is given by full load current square IFL. IST indicates the IST is for starting current. IFL indicates the full load current. When the full load is applied on the machine, at that time what could be the amount of current drawn, that is indicated with the letter IFL. So IFL indicates full load current, IST indicates the starting current, right? Now the full load torque, the torque at full load is given by I full load square into R2 by SFL. SFL indicates the SFL indicates the slip. In our entire discussions, slip at full load. Slip at full load. So SFL indicates the slip, IST indicates the starting current, IFL indicates the full load current. Now, if you take the ratio T starting by T full load, will give you the I starting current by I full load current square into SFL, the slip at full load. This is the relation between the starting torque and full load torque if you are using a DOL starting method, direct online starting method. But dear students, using this method, what is the drawback? At the time of starting, it is going to draw huge amount of current, which will be around 5 to 7 times the full load current. 5 to 7 times the full load current. That too, it all happens for a short duration of time, right? So this is the DOL starting method. So what is the next method we are having? Next one is the stator resistance or reactor method. Stator resistance or reactor method. What they will do is, instead of directly giving the supply to the stator winding, in between the supply lines and stator, they will connect a rheostat or reactor. They will connect a rheostat where we can vary the resistance. So by what happens is, by varying the resistance, we can control the current drawn by the machine, current drawn by the motor, 3-phase induction motor. So instead of applying the full current, right, only some fraction of the full load current will be applied. So by controlling the supply voltage, only some fraction of voltage of the supply voltage will be applied at the starting of the induction motor. This is very, very important. All this will be achieved by just simply connecting an external by adding some resistor just to control the supply voltage. Simple. For example, here if you are having a source which is giving you some 220 volts, and if you are having a load, right, if there is no internal any external resistance is connected, this 220 volts will be directly applied to the load. But if you have connected for example, if you have connected any resistor in between the source and the load, because of the resistance, some current will flow through this one. This entire 220 will not come to the load. Some voltage V equals to, depending upon the current flowing in the resistor, V equal to IR, amount of voltage will be dropped. So out of here, only 220 minus V will be 220 minus the drop is V. 220 minus V, amount of voltage only will be applied to the load, right? So that means but just simply by adding the resistor or reactor, you are controlling the input voltage. Only some fraction of the voltage will be applied to the induction motor. Now this fraction X will be always less than 1. This fraction will be always less than 1. So due to the drop in voltage, starting torque also will be decreased. The starting torque also will be decreased. Instead of using the rheostats where the entire power will be wasted, the losses will be more. Because of the resistor, there will be losses, right? And because of the losses, the efficiency will come down. So instead of using resistors to control the voltage, it is better to use a reactor. It is better to use a reactor. An inductor found in the form of a coil. Reactor better is to prefer. Now the torque, already we know that from our previous discussions, the torque is given by current square I square by omega s into R by S. Now if you take the starting torque by full load torque, TS indicates the starting torque, TF indicates the full load torque. Now TS by TF equals to I starting current by I full load current square into SF. As I told you earlier, SF indicates the slip at full load, right? But are we going to apply the entire voltage? No. So because of that, only some fraction of starting current only will be drawn by the machine. So X times IS only will be drawn. X times IS, amount of current only will be drawn by the machine. Now in the place of IS, is is only just some x times is, the value of x will be less than 1. So T starting torque by T full load torque will be now equal to is by if whole square into sf into x square. As this value of x is less than 1, so now the amount of starting torque has been reduced. The amount of starting torque has been reduced, right? So this is one way, this is one method of controlling the what is this starting method of the induction motor, stator resistance or reactor method. The third one is the auto transformer. In DOL starting method, what we have done, where we are having the three-phase supply lines, from there directly we have given the supply to the stator. Directly we have given the supply to the stator without controlling any level of voltages. Directly we have given. Because of that, what happened? It is going to draw the huge amount of starting currents. Now by using some intermediate device, auto transformer, instead of directly giving the supply, we will control the amount of voltage given to the stator winding. We are going to control the amount of voltage given to the stator winding. Auto transformer, it controls the it will be given the three-phase supply. Output voltage will be given now to the stator winding. Output of the auto transformer will be given to the stator winding. So because of that, now only some small fraction of voltage, only some small fraction of voltage will be given to the stator winding. Some x times V1 voltage only will be given. Because of that, now what happens, as the voltage level has decreased, the amount of current drawn will also be only some x times the starting current. So using auto transformer, what we have done now, we have reduced the voltages. The auto transformer is a step down transformer, reduces the per phase supply voltage, and it will we will apply, instead of V1, just simply we will apply some x times V1. Because of that, the amount of current drawn will be reduced. After the motor reaches, it will not be forever like that only. After the motor reaches its normal operating speed, slowly the auto transformer will be disconnected and the full line voltage will be applied. Once the motor has attained its normal operating speed or its rated speed, what happens is, slowly this auto transformer, you will have the variable knob. Slowly we will bring it down to its normal value, 0 position. Like this we can control the control the induction motor. So here also, from our previous basic, starting torque divided by full load torque, TS is the starting torque, TF is the full load torque, is equals to the starting current IS by I full load current square into SF. SF is the slip. How do you understand the slip? S equals to ns synchronous speed, ns minus speed of the rotor divided by ns percentage of slip into 100 is the percentage of slip. From our previous discussions, if you recollect, okay, if you are having a stator like this and if you are having a rotor like this, for the stator what will be given? Three-phase supply will be given. Because of the three-phase supply, some resultant flux phi r will be established. Now this flux phi r will be sweeping the surface of the rotor with some synchronous speed ns. But if the rotor rotates at the speed n, now the difference between these two speeds, ns minus n divided by ns into 100, is called the percentage slip, percentage S slip. So full load slip, at full load, what could be the speed of the rotor? ns will be constant, synchronous speed will be constant. But if for example at fully loaded condition, if this ns is almost becoming equal to the ns, then this difference will be low. The value of slip will be low. For example, if n equals to 0, for example, if a rotor is not at all moving, if n is stationary, n equals to 0, then what happens? Slip will be 1. If n speed of the rotor is 0, then what about slip? Slip will be 1. If rotor is moving at synchronous speed, if n equal to ns, rotor is also rotating at synchronous speed, then what will be slip? S will be 0. But in induction motor, it will never attain the synchronous speed. The rotor will never attain the synchronous speed. It will try, but it cannot attain the synchronous speed. But if in case if it attains, then all of a sudden slip becomes 0. Slip becomes 0. Right? This is not required here, but just to make you understand why the importance of slip S. What do you mean by slip? You have to recollect our previous basics. Ns, percentage of slip, is given by ns minus n divided by ns into 100. Ns indicates the rotating or revolving magnetic flux speed, synchronous speed. N indicates the speed of the rotor. Speed of the rotor. Right? So here, as we are applying only some small fraction of voltage, some x percentage of V1. Now the current also will be some x percentage of Is. So here Is T starting torque divided by T full load torque will be equal to Is divided by If starting current by full load current square into SF slip at full load into x square. So this is the starting method using the auto transformer. You can observe here the winding is connected in the star manner. It is connected in the star manner. Here root 3 times VL. Voltage in between the two lines. Line to line voltage is root 3 times V1. This V1 is the phase voltage. If you measure the voltage in between this neutral point and any one of the line, we have assumed in this case as V1. Now the line voltage, the relation between in star connection, the phase voltage will be equals to the line voltage divided by root 3. This is the relation. So here in this context, what is the line voltage we have taken? Root 3 V1. So phase voltage will be root 3 V1 divided by root 3. So it will be simply V1. V1 is the phase voltage. Like this you have to understand. Like this we have to understand. Right? Now the other method is star delta starting method. Star delta starting method. Here we will have a three-phase supply. This is a three-phase supply. Right? We are having a switch here ABC and triple pole double throw. Triple TPDT. TPDT indicates triple pole double throw switch. Triple pole double throw switch you are having. Once if it is at position 1, these connections will be made into the star manner. If it is at position 2, the same windings will become in a delta manner. So at the time of the starting, the windings will be in the star connected mode. Slowly once it has reached the steady state or attain its speed, right, now it will be switched to the delta connection mode. It will be switched to the delta connection mode just by handling this switch. Double throw switch will be there. Just by changing its position, you can make one time in a star connected mode and another time in a delta connected mode. Because of that, what happens? This method is used for motors designed to operate in delta connected winding. Right? The stator phases are first connected to the star with the help of the triple pole double throw switch, that is marked at position 1. This is at position 1. When the steady state speed is reached, now the switch will be thrown to position 2. The switch will be thrown to the position 2. So because of that, at starting stage, the current will be equals to the ISS. ISS indicates the starting current during star connection. Starting current in star connection. ISS will be equals to the VL by root 3. VL by root 3 divided by VL by root 3 into Z. Now the same starting current in delta manner, it is given by root 3 times the starting current in star manner. For example, if starting current in star manner is 1 ampere, the same starting current in delta manner will be 1 into root 3 is around 1.73 amps. Will be 1.73 amps. That much difference will be there for the same current, whether it is delta connected manner or star connected manner. So here the starting current in delta connected manner will be root 3 times the ISS. So from our previous discussions, T starting divided by T full load, T starting torque divided by T full load torque at full load is given by 1 by 3 into ISD divided by IFD. Starting current divided by full load current in delta connected manner square into SF. So this is the way of using a star delta starting method. Another one also is there where we are going to control the rotor resistance. As we have discussed earlier, we are going to have a stator and rotor. Rotor is also will be having a three-phase winding, right? Now the resistance of the rotor now R2. So far we have indicated the rotor resistance with the variable R2. Now for this, if some external resistance is added, now the new value of resistance you can treat it as some R2 dash, where R2 dash indicates the already existing resistance of the rotor plus some newly added resistance. So for the rotor winding, right, by some external means we are going to add some resistor. Now because of that, now the rotor resistance will be treated as some R2 dash, where it will be equal to R2 plus R. So here this will decrease by adding this external resistance, what happens is this is going to decrease the starting current. Very, very important. By adding some external resistance, you have controlled the starting current. So and this will decrease the starting current and increases the starting torque and also improves the power factor. The slip rings shown are connected to the rotor terminals of the wound rotor motor. At the time of starting of the motor, the external resistance will be added to the rotor circuit. Slowly, once machine attains its develops the required amount of torque or its speed, normal condition, right? The external connected resistances will be removed. Right? The external rotor resistance is decreased in steps as the rotor slowly attains the speed. However, the motor torque remains maximum during the acceleration period of the motor, right? So now the current value, the current I2 with respect to the rotor, the current drawn by the rotor will be given by actually some impedance voltage. As we are familiar, V equals to IZ. If somebody asks you current I equals to V divided by Z. Z indicates the impedance. Now rotor, with respect to the rotor side, the voltage is E2 divided by impedance root over R2 by S whole square plus X2 square. X2 indicates what? X2 indicates the rotor reactance. R2 indicates the rotor resistance. And already you are familiar with S. S indicates the slip, right? So the current is given by E2 divided by root over R2 by S whole square plus X2 square. Now by adding some external resistance, our R2 becomes some R2 dash, new variable. R2 dash is nothing but R2 plus R. So now the new value of current. This is without adding resistor. After adding external resistance, E2 divided by root over R2 dash by S whole square plus X2 square. Like this we can reduce the amount of current drawn by the machine. Right? So this is all about the starting methods of three-phase induction motor. Dear students, I repeat again, we are having 5 methods. DOL, direct online starting method. This is the circuit diagram where the stator will be directly connected to the supply. The drawback is it is going to draw the huge amount of current at the starting. This is the voltage control method. This is the is controlling the voltage. Stator resistance or reactor method. Stator resistance. Instead of applying the entire voltage, only some fraction of voltage will be applied, either by adding some stator resistance or reactor. But instead of adding resistance, better add the reactor. If we have added resistor or resistances, there will be huge amount of losses. If losses are more, the efficiency of the machine will come down. So better consider the reactor, where it will be the variable. Slowly, once it attains its normal condition, the value, the reactor will be removed. So here also it depends upon the fraction, how much fraction x, how much fraction of voltage you have applied, it depends upon that value x square, right? This value will be less than 1. Auto transformer, instead of applying the entire voltage, here also some fraction of voltage only will be applied to the stator. So if V1 is the voltage per phase, root 3 V1 is the voltage between two lines. Now the current also, again here also will be only some fraction of starting current, some x times Is only will be drawn by the machine. This is the with the help of the auto transformer. Fourth one is the star delta. At the starting stage, the machine the windings will be in the star connected mode. Slowly, once it attains its normal operation, the windings will come to its delta connection mode, right? So this is how. And rotor resistance, this is by adding some external resistors to the rotor. Without adding resistors, the rotor resistance is R2. By adding some external resistors to the rotor, R2 dash. So R2 dash is nothing but R2 plus R. By adding some extra resistor, the amount of current drawn will be reduced, right? So in the next video, we will discuss about the brake test of 3-phase, brake test on 3-phase slip ring induction motor, right? Thank you.